Hey everyone, my name is Simmer Work. I'm an associate professor and extension specialist with Auburn University, primarily work in the precision ag and machinery systems area. And today I'll be talking about spray drones and a little bit of on the drone seeding, providing a little bit of current research we're doing, and also some of the opportunities, challenges that are in this space. So I'd like to start with, if you've been following along on some of the spray drone um, in the ag side, that we have a lot of activity in the last 3 or 4 years where every farm show or event you go to, you don't you kind of see different platforms and the spray drones everywhere, and they're different. They're getting bigger and bigger. I can say last 3 or 4 years. But it's not just that the industry is picking up on this side. We have also seen a lot of interest, not just from, I've done a lot of events for schools and all that, but more or so, even a lot of interest among the growers or applicators in the ag industry on what the potential is for the spray drones. So to kind of provide a little bit of background, currently as we have, there are different spray drone options in the market. You see some pictures here, some of the major players are, of course, DJI is one of the big ones. Then we have Helio, XAG, and there are some of other brands, and they have some of their unique platforms or design. Some have nozzles, stacked under the nozzle or on a boom and stuff like that. So there are different options available today in the market. And just roughly, if we think about the cost, what it might cost, is anywhere around 30 up to $50,000 in that generic range. And we have kind of seen, even with the newer models coming in, it's not, we're seeing a higher price for as the technology advances. We're probably staying in somewhat same range, but the models or the capabilities of these are improving significantly, as I can say. Other thing to kind of notice on some of the common specifications for these spray drones is, we started with 4 or 5 years ago, we had a pretty small tank, and some of these are still available, but we have gotten bigger and bigger. I think the biggest one we have is about 18 gallon. But it's, again, there could be a model tomorrow that may have 20-gallon tank on it. On the spray system side, what we have seen usually, there is a pump or two pumps, or could be more, depending on the manufacturer. But we're seeing these are low capacity electric pumps, and then some sort of nozzle configuration. And this is where they vary from each other by manufacturer or models, where there could be just two nozzles, four, as much as maybe 12, or the newer trend in some of this is also rotary atomizers, which we're going to talk about here later. Spray volume, again, this is an aerial application platform, so most of the volume is going to be in line with that aerial applications of about 2 to 3 gallons per acre. This is also kind of limited by the pesticide label. So if a label says a minimum of 5, then that's kind of our required gallons per acreage over there. Spray swath is again dependent on also the model and the height, right? But some of the bigger platforms are able, their claim that their spray swath is a little bit wider than the smaller, but also very much dependent on height. Like I said earlier, most of the height were ranging from 10 to 15 feet. And then from the battery life, most of these, that is kind of also one of our bigger limitations, but we're getting anywhere from maybe 5-10 minutes, maybe stretching it. If you have a full tank and all that, we might be give 7-8 minutes max. In some cases, maybe up to 10. And then productivity all goes back to, that's why I have a range here, because are you spraying 2 or 3 gallons? How many times we're landing, refilling, recharging, and stuff like that. So it could be anywhere from 20 to 40 acres. And I see some of the manufacturers may even claim a little bit more acreage than that. But just some general specifications there. And then before we dig too deep down into, because I'm not going to cover in detail any of the rules and regulations, but just wanted to highlight that this is these operations, spray drone operations, are very different from us just flying a drone with a camera, taking pictures and stuff. Most of these platforms today are greater than 55 pounds in weight, including the payload. So we have to have different or certain licenses and certifications. We obviously want to have our Part 107, which is just a certificate to fly a drone. But then we got a Part 137, which is for agriculture aircraft operations. Then we got to have exemption, your state's commercial pesticide applicator license, a FFA drone registration, a third class medical, all that. So there's a bunch of these things. Again, I'm not going in detail, but do want to mention that anybody interested or doing these operations needs to have all those licenses and certifications. The best resource I can point for right now is the FAA has a very special section on their website just for dispensing chemicals and agricultural products with US or drones, and they have pretty detailed information on some of these for anyone who's interested in that. All right. So what are some of these? What are spray drones used for? Right, pesticide applications, or why? Just want to go through why so much interest in this technology. Timeliness is one of the big things. Obviously we do have a good bit of pesticide applications happening, with manned aircrafts and all that, but we do get every year in the season. Corn is even canopies taller where you don't even have an option of a ground sprayer unless you have a high clearance. But when it's timely and you don't have any other option available, feel like it can be another tool to get a timely application in. We also have, interest or increasing applications in fields or parts of the fields where if it's, right after rain too wet, or parts of the field where we may not even get our conventional ground equipment or traditional equipment, it allows us to take care of those parts, go spray those parts of the field or the whole field if it's in around tree line, between the power line stuff where we're not very comfortable doing applications anyway. And then especially, we also are seeing more and more where, like I said, small irregular shaped fields where there's a lot of turning around, or you can't even get a larger boom sprayer and not very efficient. Spray drones could be a little bit more efficient in spraying those small and irregular shaped fields. Now, what are we seeing some of these applications? What type of applications? So, of course, spot spray herbicides. I wouldn't say it's a great tool for a broadcast herbicides or anything like that. Obviously, chemistry is a big deal there, but we have seen interest in spot spraying, whether that's an in-season weed escape or something that you need to take care of, and you don't want to get your ground sprayer to treat just for that or the whole area. You just want to take care of small part of the field. So that is a pretty valid application or a good use of drones for doing that. Fungicide applications has been one of the most or the top uses of spray drones, and especially more so in corn, soybeans, and even down south here for us in peanuts or cotton to some extent. And then after fungicides, we're also seeing a lot of defoliation or desiccation. We're seeing desiccating soybeans with the drone and all that. And then we're also seeing defoliating cotton, and any other in season where the label require or label has a aerial application on it, and you can kind of go and make that application. And we're also seeing some other applications as applicable here and there. But from crop standpoint, especially row crops, of course, corn fungicide applications, desiccation or fungicides in soybean, cotton defoliation, even to some extent peanuts down here. And then also some specialty crops, because those are small acreage, high value cash crops where, we're not concerned about spraying 50 acres. It may only be 10 or 20 acres, but some of the rate requirements are a little bit higher on that. So, as our ground sprayer and aerial manned aircrafts are already well-established methods. So spray drones are somewhat new in this area. So one thing we know that there's so much research available, especially on ground sprayers, speed, nozzle, boom height, you talk about different sort of things there. And even, we got a good bit of research available on the manned aircraft, since it's been around for a long time. But spray drones being such a new technology, we're not really sure about what type of optical or optimal application parameters should we be using, right? And then how does the efficacy look for these compared to some of the other traditional? So if you talk about those application parameters, right? Is there optimal GPA that it works well with? What is the swath width, nozzle type, height, speed, and stuff like that? So we've been kind of working on, and that's what I'm going to share a little bit of information on, that is looking at some of those parameters. And our efforts or research efforts have been focused on, different areas where what do the parameters look like? And this is, in some cases, it's maybe bare ground testing from that perspective. And then in some cases, it's also within canopy. What is the deposition look from a spray drone within canopy from here? And then all the way taking it down to product efficacy, which means that how does, some of the common pesticides that we apply with spray drones perform, or what is their efficacy look when we're spraying with the drones? So to start with, over the last 4 or 5 years, again, like I said, there are different platforms. So one common thing we can look at among these platforms is uh, we got drones that have nozzles, and then we have drones that like I said, the new technology, rotary atomizers. So these nozzles are usually under the rotors or could be on a boom or something like that. And we have rotary atomizers. It's just a different way of generating spray droplets. So these are the two common platforms. And I just took examples of, like, DJI has a T30, which has a nozzle type of configuration. And then their new T40 and now even T50 are equipped with rotary atomizers. And then similarly, other manufacturers have similar platforms. These are just examples to show what these platforms might look like. So like I said, we've been doing a bunch of bare ground testing also, just look at the deposition and stuff. One thing, and I just want to make a point of, this was probably even before T30, a drone with the nozzles. This graph shows data for different GPAs, which is gallons per acre. And one thing you'll see right here is, even across the whole swath, most of that spray from a drone is concentrated pretty heavily right on the drone, right? Especially at a higher volume. As we go to lower volume, those 2 or 1.3, we don't see that distinct peak and stuff like that. But we also have a pretty low coverage. But the point I want to make here is, we talked about spot spraying herbicides. Why that is a pretty good application, or why that works well with drones. Because if you think about, when we're doing these spot spray applications, we're going to these locations in the field where these weeds are. In this case, example of this pigweed, right? And we're not spraying, or our target is not spread across the whole swath. We're kind of doing a very targeted application. And because we have a good amount of spray or coverage right under the drone, we're able to get that product out there on the target, and also see a pretty good efficacy from the target. As you can see, another example here, application with the drone on pigweed did a pretty good job of, killing them. But if you think about most of the other applications, when we're doing with a drone, are broadcast applications. It's not a spot spray where we're only going targeted. It's we're trying to cover the whole field acreage or the whole area, right? So for broadcast applications, we need to make sure the way the spray drones work, that we have an adequate overlap from the adjacent passes, which means you can't just make a single pass and assume that we got a pretty uniform application across the full swath of that drone. We actually need overlap from the passes from each side of those pass to make sure that we have a uniform application. So what that means, or what may look like, is if you look at the graph, I have a single pass and the pattern may look something like that. I need to make the other two passes on each side. So the actual spray across the swath looks something like this, which is more uniform than a single pass. And the spray swath is also less than the single pass swath because it's an effective swath. What an effective swath is the widest possible swath that we can minimize the variability. So that's why when we talk about drone broadcast applications with spray drones, we need to make sure we consider this effective swath, not just what's the widest possible swath, single pass swath with the drone is, right? So next, I'm going to share a little bit of data, what we've been collecting, and more so here with corn fungicide studies. We did this year and last year. And I'll also specify the platform here because, again, each platform has a very distinct spray characteristics, pattern, or behavior. So we cannot say that you can replicate the same results, or we may get the same results with another type of platform. But we can start to pick up trends among some of this data, and that's what I'm going to focus on. So in this study, what we did was we started this when T30 was predominant, which has nozzles under it. What we wanted to do was spray two different spray volumes, 2 and a 5, 2 being a common aerial volume, and 5 a higher one. And we did 4 different heights over the corn canopy. And then the other thing we wanted to do was assess or look at the deposition at different positions within the canopy. Of course, when we're applying fungicides, our goal is to get that product to the ear or ear leaf of in the corn. So we put a spray card right at the ear leaf, and then we also did a card 2 leaves above and 2 leaves, and we called that a top and a bottom position. And of course, we have a middle position in the canopy, and we made passes, replicated passes with the drone over in the canopy, and we did this across the whole swath, which kind of varied with the height. Uh, so if you look at, if you want to look at where the cards look across the swath, so this is where the drone flew, right in the middle. And of course, this is at the very top of the canopy, which means the canopy did not have any interaction yet with the drone or with the spray. These cards were at very kind of top of the canopy. You can, of course, see 2 GPA, again, 2 gallons per acre, had a little bit less deposition on the top, whereas with the 5, you can see we had a little bit higher deposition. But something else, if you pay a little bit closer attention to these cards, you can notice is for both 2 and especially more so for 5, most of the spray or higher coverage is actually towards the middle of the swath, which is right under the drone. And that's what our data showed here. If initially you just compare the 2 volumes we sprayed, 2 and 5, you see that with 2 GPA, and this also kind of follows some of the results of one graph I showed earlier for a bare ground testing, that when our volume was pretty low, 2, we not, it is a little bit more distributed because we don't have a lot of extra volume behind the drone. But what we're seeing, my point of saying is, we always used to say in our conventional with traditional, especially ground sprayers, that anytime you want to have a better coverage, you can increase your volume. In this case, with the drones, we see that that is not necessarily a case, that we cannot just increase coverage across the whole swath by increasing volume, because as you can see here, that with 5 GPA, even though our volume is higher, but most of that spray is actually being concentrated right under the drone, not being distributed uniformly across the whole swath. So we're actually producing more variability within the swath, in this case, using a higher volume. We also on the height, we did not see any significant effect of height, especially at a lower volume like at 2 GPA. It's just that the height, a higher height, 10 or 12, helped us reach wider within the swath. So it helped us attain a wider swath in this case. Now, other thing I want to highlight is, well, our most of the time our assumption is the drones have a propeller wash right under the drone, which helps us get that spray within the canopy. Now, if you look at this graph, which is showing our spray penetration or deposition across the whole canopy, we can see that our 2 gallons and the 5 gallon at the top and the middle and the bottom, that we're seeing again a big peak right in the middle for that 5. It is pushing a little bit more right under the drone, but we're not getting any extra deposition across the whole swath because of that downforce or downwash. And the reason being that drone's downwash is very much localized right under the drone. It is almost, we can say, approximately equal to the width of the drone itself. Most of our spray platforms are anywhere from 7 to 9 or 10 feet. So most of the time that propeller wash is only going to be another foot or so wide. So we're not getting that downwash effect across the whole swath, but only right under the drone. And also, the higher the drone is in the air, the less effect of the downwash in the canopy, because it's actually using, the propellers or the downwash to fly. When the drone, you get a more downwash effect when a drone is hovering compared to when it's actually flying. We don't see that much of an effect. But when we look at the efficacy, right, also want to show for 2 and 5, we did this in plots. You can see on the table here, we did disease ratings, for tar spot, another corn leaf blight, southern corn rust, versus we also have an untreated control here that we actually see both 2 and 5 GPA had a better control of the northern leaf blight and southern corn rust compared to the untreated check. There was no difference between the two volumes. Also, when we look at the yield across these plots, there was no significant differences between even the untreated and all that in this study. The other study we did looked at, well, how does a drone compare to a fungicide applied with a manned aircraft, right? So this was done at another site, and please note here that this was a DJI T40, which had rotary atomizers. The data I showed earlier was for a T30, which was with the nozzles. So here we actually applied fungicides in large blocks in a commercial field with a spray drone at 2 gallons and an airplane at 2 gallons. What we also did was very similar to the previous study, put out cords at middle, ear leaf, top and bottom within the canopy to look at deposition from these two methods. So I'm just kind of combining both this data. One disclaimer I want to make here is, of course, the airplane had a widest swath, which was 60 foot, 20 rows, whereas we were only covering 10 rows, 30-foot swath with the spray drone. But right in the middle of this graph, row 10 and 11 is where the center of both the plane and the spray drone was. So if you look at top, middle, bottom as it's stacked on this graph, we do see the drone did have a little bit higher deposition with those peaks right in the middle of the graph, right, from the drone, whereas the airplane, it was somewhat similar across the whole swath. But when we averaged out across the whole swath for both methods, we did not see any statistical differences. Also, if you see the peaks bigger right at the top because it's at the top of the canopy, and as we move into the canopy, the middle and bottom, it's getting less and less, so more comparable to the plane over there. Overall, we did not see significant differences across the swath between both methods. In this case, we also did the disease ratings and yield. Fortunately for the grower, maybe or so, no disease was present in this field or occurred or arrived in this field. So we weren't able to have any disease ratings, that were significant enough among the treatments, and there was also no difference among the yield. Now, one thing I want to make sure, this was just example of a couple of years of trials from different drones, but one thing we're starting to pick out between the nozzles and rotary atomizers, if you can notice, is that the blue line here is for the T30 with the nozzles, and then the T40 is the atomizers. We're starting to see that the drone with the nozzles have a little bit of a higher peak in the middle compared to when we look at the atomizers, it tends to spread the spray a little bit more within the swath with not as prominent of a peak in this case, or between the two. So this is one trend we're seeing across multiple data sets we have collected over the last 2 or 3 years. This is actually a slide because I only focused on height. There's a lot of height, rate, volume, stuff like this. My colleague, Dr. Steve Lee, is also doing a lot of data on some of the other factors that can affect, like an addition of a drift reducing adjutant, DRA or no DRA, and some of his data showed that we can even improve canopy penetration with the DRA in some of these cases. Now, based on our data or some of our research for the last 2 or 3 years, some of our journal application considerations for applicators or growers are, we want to make sure that we're selecting proper flight settings and making those application under favorable conditions. So it's not like when the wind's 8 or 10 miles per hour, we're going out doing a drone application, because again, it's not going to be very effective. And then, again, like I said, most of the time that pesticide label is going to dictate the minimum spray volume, whether that's a 2 or 3, in some cases, maybe up to 5. But the effective swath is, we need to do some sort of swath testing to make sure that we know what is the effective swath. We don't want to take the swath listed by the manufacturer that this drone can spray up to 33, 30, or 36 feet. We want to do our testing to see what that swath is. And most of the time, to be safe, what we have noticed, the effective swath is mostly 3 to 6 foot less than the manufacturer. Again, this is a very rough estimate, and that's why we want to make sure that we do our testing to make sure that what is that actual effective swath. For efficacy, again, there's a lot of research happening right now on the proper product or chemistry selection, because that definitely is a big factor. But there's also considerations of using surfactants or DRAs to make sure that to improve the efficacy of the product. And last but not least, again, there's a lot of things need to be considered. We're make sure that we're following all the best management practices, the BMPs that we usually have, whether we're applying with a ground sprayer or aerial sprayer, for a judicious use of pesticides, but also for using the drone technology effectively. I've gotten a lot of this question, in the last, especially with more interest, because some people tend to think, well, I'm going to replace my ground sprayer with a drone, or it takes away the aerial. And from my perspective and personal opinion with research and been working with this over the last few years, what we usually emphasize on, that the drone is not something that is going to replace our other traditional methods, but it is there to complement them. So it's another tool in the toolbox that we can utilize for our crop management, crop protection application needs. And just like we would pay attention to whether we're spraying with the ground sprayer or manned aircraft for a drone sprayer, we would also consider the same thing as perform a proper calibration, whether that's rate or swath testing, our application parameters, what is our risk to drift of the application we're doing, what are our regulations for flying drones using, stuff like that. Now, some of the challenges and limitations as it relates to drone sprayer, Uh, of course, rules and regulations is a big one. You can't just go buy a drone and start spraying with it. You need to make sure that you are taking care of all the certifications and licenses, and that's some time for someone who want to start their business within the next month is a challenge in a way, because you need to start this 6 months or even a year before you actually want to get out on the field and start doing this, to make sure that you have all your ducks in a row to be able to legally use drones for these applications. And these rules and regulations are also changing pretty fast. The other big one is we have established methods and procedures for performing calibration on our ground sprayers, or I believe same for our manned aircraft. But when it comes to drones, when it's a nozzle, yes, we can do that. But the lack of, we don't have any pressure gauge on these drones, to be followed, like what spray pressure should be at, and can we adjust that? There's not a lot of things you can really adjust, but more or so just verify what the drone is actually doing. Same goes for swath testing. We got different methods, whether we're doing a discrete sampling, we're putting different spray cards across the swath. And it's not an easy job for in any sense, right? It does take time and effort, but that's how we're going to make sure that our drone is calibrated and we know what the effective swath is. Other big, I would say, challenge or limitation right now is our battery life is still pretty limited. If you think about when you're spraying large scale fields, every 5 or 6 minutes, you're landing, refilling, recharging, got to have a generator on site to keep charging and stuff like that. And then the same goes, you got to have some sort of nurse tank or refill station. That way, when you're doing these large scale operations, you're equipped to keep going and not, to be more efficient in the field than wasting time refilling, recharging, and doing all that. Our other challenge is how fast the technology is advancing. Just between last 3 or 4 years, it has advanced so much that we're in our program, we're on our fifth drone now, because we started with a very small 2.5, 3 liter, and now we have a T40 and looking probably about T50. But if you think about how fast it's evolving, and each platform has its own characteristics, maybe a little bit different spray behavior and pattern and stuff like that, but we're constantly learning and applying this, right? So that's one of the challenges in a way, but other one is also from the regulations in a way, from even the pesticide labels. If you think about it, right now, for spray drones, we're just operating under, if the label has an aerial application on it and it has a minimum volume requirement, all that, as long as we're able to meet that, you can put that chemical in a spray drone and go out and spray, right? Well, what we're noticing is that there is a difference between applying something aerially with a manned aircraft and versus a drone. And so does that require down the road a separate label or separate requirement for drones on the label versus manned aircraft or something like that? Because we're seeing more and more interest in aerial applications with drones. It's how do our labels going to evolve or change down the road will be another thing to kind of keep following up on. And then I've also gotten some questions, because one thing we have relied, especially, from being kind of involved in this almost 3 or 4 years, spray drone is not something that a grower's going to buy and just start spraying on his own farm, except for maybe some progressive growers. Needs a dedicated effort almost. So what we're seeing, this is more like a business model for people or applicators, just like manned aircrafts, that people who want to offer this as a commercial service to other growers, right? And then we've gotten questions about some of these, and I've just listed very main points on, you need at least minimum 2 to 3 spray drones. You can't just rely on one, and if it goes down, your business goes down or you're not making any money. Gotta have at least minimum 2 people, not just from the operation or logistics standpoint, but also because our rules and regulations require that one person constantly needs to be a visual observer or need to be following the drone while the other is, operating, have a remote control and stuff like that. Uh, and this is again me minimum 6 batteries. I've seen people with 8 or 10 batteries per drone or per operation. Generator, nurse tank, how you gonna haul that, to the field, to the site, back and forth around. uh, uh, so may require some sort of trailer setup even to watch the drone while it's flying as a visual observer. And then want to make sure all your licenses, certifications are covered. Insurance and liability is becoming a big deal because, like I said, this is almost like a 30 to 50. So if you think about it, almost like us purchasing a car or a vehicle or a truck, right? Where we need to make sure that if something happens, we have insurance on it to replace that without it costing us too much. And then this is a very rough number. If you're just starting to think about maybe a 1 or 2 drones, like I said, two is minimum in a way with some trailer setup and a few other things, you could be looking at anywhere from about 120 to 150K minimum just to get into the spray drone business side. And there may be some other maintenance or other costs. You may want to have spare parts and all that on hand to be able to operate without any hurdles in the season. All right, the other aspect I want to cover from the drone standpoint is that most of these spray drones or drone platforms also come with a spreader system, which means, as you can see in this slide, that we can actually take the solution tank out and swap it with a dry spreader box. And as per the companies or the manufacturers, claim that these can be used for application of dry, small, solid materials. One of the biggest applications, again, being very small seeds, which our case is cover crops with these. And I've also seen or heard about some granular fertilizer applications in the season. So if you look at it, has picked up, of course, the spray side with the drones picked up earlier with more and more interest. And within the last year or so, we're seeing more and more interest in seeding with drones, especially cover crops. Some of the things we think about why or advantages is timeliness is a big thing, right? Again, there's some research that suggests the earlier we get our cover crops established in the fall, we get a better stand establishment and more benefits. So timeliness, when we think about right now, is we have the ability to go and spread cover crop seeds or cover crops even when the crop is still there, even before harvest. Most of the time, this is usually, if you're doing it with a traditional equipment like a drill or something, you can't get in until the crop is actually being harvested. So that's one main thing that we're getting more and more or seeing more and more interest in this. The other also goes back to the spray thing, that we have fields or part of the fields where, especially if it rains too much during harvest or late in the fall or winter, we really can't get out with a tractor or a drill in there. So we still have a potential to go out with a drone to be able to go and broadcast this. And then I've also just put supplemental because I've kind of noticed or heard about people doing some almost called spot or targeted applications, because we can't put out a lot of rate, pounds per acre with these systems. But I've seen some people applying urea or small rates, targeted applications in some fields. And then recently, I also talked to a couple consultants or growers who were thinking about applying some micronutrients, especially because our rates are so low on these that these are actually able to handle those. So one of our goals last year or so also has been looking at the application performance of seeding drones. So in this case, I'm going to use example of this DJI T40. Most spread systems on these are pretty similar, where you have a dry tank and a rotating disc under it which is spinning in one direction, just one disc spinning and broadcasting that. So for this drone, we had a tank volume at 70 liters, but if we think about the load, it can take about 110 pounds of dry material. Again, that's going to depend on the density and what material. And as per the manufacturer, DJI in this case, they said that we can have a spread width up to 7 meters, which is roughly about 22.9 or 23 feet in this case. So what we did was we actually utilized rye, cereal rye, as that is one of our most common cover crops being spread across the US, I can say. And then we also did a little bit of testing with urea to see what type of performance we're getting with seeding drone. So right now, our biggest, and this is again a challenge or limitation with the drone from the dry seeding perspective is it provides you a screen to perform a calibration, but there is no input or feedback on the material, what the material properties are. Because when we think about applying fertilizer or seed or other things or calibration with our drill or fertilizer spreader, we take into account the density of the material and few other properties to make sure that it's calibrated and applying the right amount of rate. But right now, the only option we have with the drone is you get to this screen like you can see on the left here, where you can add a new material, or you fill the hopper up fully, and then you kind of run a calibration test, which is basically it's opening that gate height or a gate opening at different openings and calibrating the drone. So what we wanted to do is we did that calibration, but what we also wanted to do was do our own calibration to create our own calibration curve. So in this case, we took the hopper and then we opened that gate at different gate openings from 10 up to 100% to actually determine what is the actual flow rate in pounds per minute, kilograms per minute, whatever unit we want to use. But what is that flow rate? Because to my previous slide here, when the drone performs this calibration, it gets saved within the drone. You don't have access to what is the rate at different gate openings and all that. So that's why we wanted to go ahead and do this so we have actual data or actual numbers for what is the flow rate at these different gate openings. So here's the kind of graph we created for rye, which is what is the flow rate pounds per minute at different gate openings for rye, and then same for urea. But our intent is, so here's our formula where how many, if we want to put out certain pounds per acre, you have a flow rate. What is the drone putting out in this case? Pounds per minute. We have a calibration factor or a calibration constant, which is just the units conversion and other things. But then speed and swath. So in essence, we could be looking at the drone. We could punch in our target application rate here, let's say 20 or 40 pounds, and back calculate what the flow rate should be in minutes, pounds per minute. And then I can go back to the graph and say, well, it's saying that I need to have, in this case, a flow rate of 100 pounds per minute. And if I go on my horizontal axis, roughly, it's telling me that my gate should be opening about 50% if I need to put out these many pounds per acre. So for us to verify, is it actually happening in the field or not? So the other thing we did was, that was a static testing. We wanted to do a field validation. Most of the time when we're talking about cover crop seeding with drones and stuff like that, we're talking about low rates. I'd say 20, 30, 40, nothing more than 50 or 60, and I'll show you for a reason why. So we did this where we took the disc that spreads or broadcasts the seed off, and we wanted to collect how much material the drone is actually dispensing while it is in the flight. And we did this 5 different rates, timed the application so we know how much it should be putting out. And the controller also gives us a number on what it says, because there are weight sensors under the hopper or under the box, and it's measuring that. So we did that at different rates. So this is what did the controller set our weight was, and what was the scale weight was. We took those, converted that, and this is what we saw here. So this is a very interesting graph, and I want to make sure I point out what's happening here. So if you think about it, at our lower rates, 20 and 40 pounds per acre, right? We're not putting out enough. So if you look at the table, we're off 30 to 45%. We're not meeting our actual rate. And this is common. This is what we noticed and we suspected, because our gate opening at these lower rates are smaller. It's more like 20 and 30%. So going back to our material and material properties, we noticed that the gate was bridging, so there was no consistent flow, which means that our actual applied rate is lower than what it should be, uh, than our target rate. We were finally able to meet our actual rate when we were at 60. So we're only off by 5%, which is pretty good for that. So this is where our gate opening was more than 40 or 50%, which means there was enough space there for the material to flow consistently, have a consistent flow, and give us the rate that we actually need. But then if you look at it, 80 and 100, we max out that opening. At this point, the gate is wide open. It's putting out as much as it can, but we're not able to go over. In this case, with the gate fully open, we cannot apply more than 70 pounds. So that's why we're seeing it being maxed out at those 70 points. And that the big thing is, again, there's a very small gate opening range for based on the material, and there's even different gates that the manufacturer provides for smaller, medium, or larger. This was the largest gate that we had. So that's something really to think about. The gate, the disc you're using, the metering disc, and what is the opening on that to have a consistent flow for that rate. The other thing we wanted to do was to look at not just the rate accuracy, but also what does the distribution look like across the swath, right? So in this case, we had pans placed 3 foot across the swath, and we flew drones over it at, again, 20, 40, and 60 pounds in this case. So here's the data from that. You look at it, this is all a single pass data, okay? So again, at 20, you can notice that we're not applying enough. So all those 3 passes, that dashed line is our target rate, is not meeting that. And even when we average all those, the left hand is all 3 replications, whereas our bottom one is the average rate. Again, you can see across the swath, we're not meeting that 20. Now, when I talk about, again, this was a single pass, right? So this is a single pass. Just like spray, we need overlap from adjacent passes in this case, which means we're going to have material come from the pass on each side and give us application or fill up the gaps on the edges or on the ends. So we need to find out effective swath in this case again, right? So we did that for multiple different scenarios, because we can do that when we have a single pass data. So here we took those 3 rates, 20, 40, 60, and we created simulated effective swaths and CV. CV means how uniform our distribution is in this case. So when we have lower CVs, which means better distribution, higher CV means more variability. For granular materials, we prefer CV to be between 20 to 30, 25 to 30%. And interestingly, in this case, when we look at, even though our applied rate was less, right? Even though our overall applied rate was less in this case, but our CV values were acceptable, which means that we do have some uniformity in the application within that manufacturer recommended swath of 23 feet. Now we could increase that uniformity by even going further down. We can spread it 20 feet or 18 or whatever. Lower usually provides you a better CV. The higher swath width you go, your CV is going to get worse and worse. So some of the main things to consider, again, we're doing more and more research to learn about this, but some of the main considerations here are the actual applied rate could be lower, right? Like I said, because of, again, the gate opening, the type of the metering disk you're using and all that. And it may actually need to be adjusted so you can match the actual rate to the applied rate to the target rate. And one of the limitations, again, why this is also happening is because we do not account for our material properties. Right now, all we're doing is just punching a number in the controller and hoping that it's putting out what it's supposed to be putting out without accounting for density and some other things. Drone settings, like I said, gate opening, or even the metering mechanism, like I said, right now, like if we're talking about DJI, they sell a small, medium, and a large gate for these, must be selected properly so we have a very consistent flow of material. Material bridging can, again, not only cause rate problems, it can also cause uniformity issues. And then we also recommend doing some sort of pan testing or something to verify distribution, not just because we obtain pretty good distribution with dry in this case, that everything you're going to spread with the drone is going to have a good distribution. We do recommend applicators and growers to perform some sort of testing to verify that what does the uniformity look like, and choose that swath or adjust settings that minimizes the variability between that set and have a more of a, within the swath, and have more of a uniform distribution for the material that you're trying to spread. All right, I'm gonna wrap it right there. There's my contact information, email, and phone number. If there are any questions or anything follow up, please don't hesitate to reach out. Thank you.